The forest plot is probably the most important part of the meta-analysis, or it's the most visual part of that meta-analysis, and summarises the conclusions of it. So you need to know what a forest plot is, and you need to be able to interpret the meaning of the forest plot. So the forest plot is a graphical summary of the data from the meta-analysis. Each of the summaries, each of the studies is summarised on a separate line with their effect size and confidence intervals. There's a final summary which will usually be represented as a diamond showing the effect size across all the studies. And there's a vertical line showing a summary of the effect size. Sometimes you have a second dash line if you've got heterogeneity. So here's an example of forest plot for some binary data. Here you've got the study, so that will be the first author. Sometimes you'll also have the year that they've done. This one's measuring risk ratios because that's the typical thing that you use with binary data. It could be odds ratios as well. At the bottom you've got the scale of the total calculated value and the diamonds for the fixed and random effects model. In this case both the diamonds sit over each other, so there's relatively low heterogeneity and you don't need to go to the random effects model. The zero line, meaning no effect between the two cases, would be 1, meaning the relative risk is 1. There's the same risk in both groups, and you can see here that it's on the negative side, so there's a lower risk. You've got the confidence intervals, you've got the weighting of each of the studies, so you can see that the weighting is very different between different studies. The bigger their variability, so the second study of Block has a very wide confidence interval, and so it's down weighted, whereas the Auckland study has a very low variability and therefore it's got a very high weighting. The diamond is the summary statistic of the analysis, showing you the mean for all the data and its variability. If you've got a very wide diamond, then there's lots of variability between studies. The narrower your diamond is, the more specific your result is, more precise your result is. The right hand side has tabulated values. This could actually be on the left hand side depending on how you've got your diagram set up, and the weight given to each study is important to look at any differences between the fixed and random models. So in this case the weightings are very similar with each other. Sometimes they're very different, indicating you need to go to the random effects model. Yes, so as I said before, Auckland study contributes nearly 50% of the weighting to the final diamond, and the two weights are very similar. The I-squared value is low, so that's telling you about the heterogeneity, and the p-value for it is 0.31. If it's less than 0.05, then there's heterogeneity and you might need to go to the random effects model. This is one for forest plot for continuous data. You've got the study name and the year. You've got the mean and standard deviation and the total number of participants for the experimental and the control. You've got the mean differences. Then you've got the calculated mean difference is confidence interval, the weight, and the weight for a random model. So here most of the studies are weighted equally, apart from Tadaro at the bottom, which has a much smaller confidence interval, and also November 1994, which has a slight difference. If you look at the I-squared, it's 9%. Your p-value is still way above 0.05, so there's no particular evidence of heterogeneity in that case either. So if your I-squared is very large, then you get a significant p-value. The left hand side contains the summary of the original papers, right hand side contains those things calculated by the program. In this case R, RevMan does exactly the same. The weights for fixed and random models were very similar. The confidence intervals crossed the line of zero effect only in 3 cases. So where there's no mean difference, you have that problem in Bonner 1988 and 1989, sorry, and De Benedictis, I think that's 1994. Tadaro has the largest weight, and the I-squared and tau show there's no heterogeneity in the data.